To introduce the idea of inverse functions, I first want to introduce the idea of functions as codes. And the best way to think about codes is to imagine passing a secret message. So here's the secret message. Math is awesome. So please don't tell anyone, but that's our secret message. And below I've given a little code. It's called a rotation code. And it's a rotation because what I've done is I've taken the alphabet, A through Z, and for each letter I've lined up another version of the alphabet that is also in order, but it starts with a rotation. So A starts here under T. And so all of the letters have been rotated by 7. Now how does the code work? Well, everywhere I see an A in the original message, I'll replace it with an H. So for example, in my message, I start with an M. For math, A, T, H. And so the word math gets replaced by the characters T, H, A, O. So now I have my encoded message. Math is awesome. And I can pass that message on, and my friend can now be able to interpret it. Now, rotate 7 is not the only code. So here's another example of a code. Rotate 19, the same basic idea, except what I'll do is I'll take the first 19 characters and shift them off. A lines up with T, B lines up with O, and also, for example, M lines up with F. So I could also encode my message using rotate 19. So let me do that. Okay, so here's my secret message encoded in rotate 19. But maybe what I want to do is I actually want to encode it doubly hard. So what I'm going to do is I'm going to take my rotate 7 code, and I'm going to now apply the rotate 19 code to my rotate 7 answer. So I'll start with my sequence T, H, A, O, and I'm going to encode that using rotate 19. So the T gets sent to M, the H gets sent to A, the A gets sent to T, and the O gets sent to H. Wait a second, what's going on? My second code, if I do rotate 19 after rotate 7, I'm uncoding the message. If I were to finish this, PZ is encoded as IS, and my final word, HDL ZVTL, is decoded as awesome. In other words, rotate 19 is the decoding code for rotate 7. It's the inverse. So this introduces the idea of an identity function. A function that when you do an operation and it leaves your message unchanged, that's called the identity. For the simple codes that we've been looking at, a rotate 0 where A goes to A and B goes to B and C goes to C, so every letter goes to itself, that's the identity code. What we just saw is if I first use rotate 7 on any message, and then I do rotate 19 on that message, that double encoding is also the identity. And it turns out that property that the sequence of the codes is the identity is exactly what we need to have inverse functions. So if I have a function f, a second function g is its inverse, if when you do the composition f composed with g, you get the identity function. You also have to have g composed with f is also the identity function. In other words, f and g have to decode one another. That's usually written in function notation by saying f of g of x is x and g of f of x is x. But I like to think about inverse functions in the sense of coding and encoding. So if I think about x as my original message, f encodes it. The inverse function takes the encoded message and it returns the original message. We usually think about functions as functions on numbers. So I want to show you how this works and how we can still think about it as encoding a secret message. So consider this function f of x equals 2x plus 6. I've graphed it. You can see that's just simply a line. We're going to use it to encode a secret message, which is a sequence of numbers. It's not letters, it's numbers. And so what we do is for each number in my sequence, we will look at the graph and it'll tell us what our code is. So 5 comes up to this point, which we can read off by looking at the y-axis. And so our 5 gets encoded to the number 16. Negative 2 is being sent to positive 2. Our encoded message are the numbers 16, 2, 12, 8, and 6. Now if I send someone this message, they need a way of being able to undo it. But notice that the graph that we've used has had us going from the x-axis up to the graph, back over to the y-axis. For each of these points, we go up and then over to the y-axis. If someone gets my message, they just need to go in the reverse order. So someone who's trying to decode, for example, the 16, we're going to start from 16 and we're going to go back the other direction, and we're able to find that our original number was 5. Or if I find the number 12, I'll follow in the reverse direction. I end up at the number 3. So it's possible, if they know my function, they can just go in the reverse order and they can recover my original message. Now that's the idea of the inverse. We're going to go in the reverse operations. So algebraically, you've probably learned how to find the inverse function. Typically, what you're taught is you create an equation y equals 2x plus 6 for us. You might have had some teachers tell you to switch the x and the y, but I think it's really important not to. I want to remind you that we're thinking of x as the original message, and we're thinking about y as the encoded message. So what we really want to do is we want to solve for x if we know y. That is, if we know the encoded message, y, we want to be able to recover the original message. If I start with y equals 2x plus 6, we'll start by subtracting 6, then we'll divide by 2. This suggests what our inverse function should be. If I know y, we take the formula y, subtract 6, and divide by 2, and that will be our inverse function. Now lots of times in algebra we always want to think about our input variable as x. There's nothing special about x. But if we were to do that, everywhere we see a y, we would replace it by x. That's how we get our inverse function. So now let's look at our encoded message. So our encoded message were the numbers 16, 2, 12, 8, and 6. And if I use my decoding function, my f inverse, I could do the inverse of 16 is 16 minus 6 over 2, so that's 10 over 2, which is 5. And I could do the inverse of my second number, 2. 2 minus 6 over 2 is negative 4 over 2, negative 2. And so you can see that we're actually recovering our original message. The decoded version of 12, 12 minus 6 over 2 is 3. The inverse of 8, 8 minus 6 over 2 is 1. The inverse of 6, the inverse of 6 is 0. 6 minus 6 over 2 is 0. And so we've created our inverse function, our decoder. Now, officially, the way that we see if a function is an inverse is by doing a composition and seeing that it's the identity. So what I've done is I've taken the inverse function in a different form. If you remember what we did, we just solved our inverse function and we got x minus 6 divided by 2, and I've just rewritten it as dividing each term by 2, 1/2 x minus 3. So let's say you didn't notice that, and we're just told the inverse function is 1/2 x minus 3. We can see if they're inverses if I think about the composition. What happens if you take a composition f inverse f of x? So this means let's take the f inverse function of the value we get when we take f of x. So we'll use substitution. Everywhere we see f of x, we will replace it by its formula. So we get 2x plus 6. Now the inverse function takes our encoded message, and whatever the encoded message is, it will put it in the spot where the x is in the formula. Notice it's a substitution. So what we're going to do is we're going to replace the x, 1/2 x, will be replaced by 2x plus 6, and then we'll subtract 3 from that quantity. And now the magic starts to happen. We use the distributive property. 1/2 times 2x is x. 1/2 times 6 is 3. Minus 3, and amazingly, 3 and negative 3 cancel. That's the identity. We get back our original message. Let's do the other composition. F composed with F inverse says let's encode the decoded version of some message. So we're going to encode 1/2 x minus 3. Now this time, 1/2 x minus 3 is going to be placed in the position of x of our original function. So we get 2 times the quantity 1/2 x minus 3, that was my input, and I'll add 6. Again, using the distributive property, multiplying over addition, 2 times 1/2 is 1, so we get x. 2 times 3 is 6, so we subtract 6 and add 6, and again, negative 6 and 6 cancels. I get back to my original message. I've just found that composition of these two functions gives the identity. So they are indeed inverses. Inverses are decoders. If I take a function and think of it as encoding a number, the inverse function recovers the original.